Paul Wright from Merlin is going to give us a presentation. Paul is an aeronautical software and systems safety engineer with over 15 years of experience in the aerospace industry. He's a chartered engineer with IET and holds a Masters of Software Engineering from University of York. Paul has experience as both a developer and a military regulator and has worked on military, civil and certified systems across Part 23, 25, 27 and 29. So, welcome Paul.
Thanks. All right, afternoon everyone. I appreciate I'm the last presentation of the day and I'm standing between you guys and beers. And it's going to take me a few beers to get the image of John dancing with his pants off out of my head. So, yeah. So I'm going to talk about assuring AI, and what I mean by that is I'm talking about development assurance, the thing we use when we're trying to get software flying. But when I talk about AI, I mean things that are developed or software that's developed through machine learning, which is a different way of developing software than we traditionally do, which is writing a bunch of if statements and logic. So if you've used the internet the last couple of years, you will have seen one of these. This is called a captcha or a recaptcha. The idea of them is that they are supposed to filter out bots from entering data into websites, maybe spamming them, and let humans through. Unfortunately, bots are about 15% better than humans at getting these right, so they really let bots in and humans out. So why do they keep using them? Well, we're feeding labeled data to Google's self-driving startup Waymo, so that when it's driving around on the roads, it knows what it's seeing, and they can train those cars to drive better. So really, you're just helping Google out, the startup. So what are we going to talk about? We're going to talk about software, just so we know what we're talking about. We'll then talk about software assurance and how we get software flying. And then we'll talk about AI and machine learning and what we're actually talking about in that space. And then we'll smash those two things together, and we'll try and do assurance on AI, where that can work in aerospace and where it breaks down. And just so we know what we're talking about, I'm talking about development assurance here. So that's a part of the puzzle piece of dealing with complex systems in aerospace. I'm not really going to talk about general certification, human factors, system safety, and they all sort of work together to make the overall system work. So I spend a lot of my day talking about software, and we're talking about a lot of things, and I spend a lot of my time writing love letters to CAA about software. Sometimes we could be talking about the requirements and what we want the software to do, and we express that as generally as some sort of shell statement or something like that. We could be talking about the code that the human writes or maybe uses a tool to write. We could be talking about the binary or the machine code, which is what a compiler takes the source code that the human's written and turns into a bunch of ones and zeros. Or we could be talking about those ones and zeros once they're loaded into an aircraft. And when we're talking about those ones and zeros loaded into an aircraft, we can't actually see or touch or feel that software. When we see a digital display or a light or an actuator move a flight control surface, we're actually seeing hardware, but we're seeing software behavior. So I like to describe software that goes flying as the actual function exhibited by hardware over which the software has control, whereas the intended function would generally be the requirements of the things we wanted the software to do. So the certification requirements that apply to software in the general sense, in the 23 space where I operate, is 23.25.05 and 25.10. And these are similar to 13.01 and 13.09 in the other domains. So 25.05 says, when installed, each item of equipment must function as intended. And if we take that actual function versus intended function type view, we can see that the certification requirement says that these things must be equivalent or the same. And 25.10 is our failure of normal operation and our probability to severity targets, catastrophic, extremely improbable, and so on. Where we have simple hardware, we would normally have quantitative targets, 10 to the 9, 10 to the 7, that sort of thing. Software doesn't fail probabilistically, it fails deterministically. And so software failure of normal operation is when there's an unacceptable gap between that actual and intended function. So when the aircraft is around flying, the software does something we didn't want it to do. or it doesn't do something when we want it to do something. And so the accepted means of compliance for software and airborne electronic hardware is a process we call development assurance to address that gap between intended function and actual function. So what is development assurance? Well, the accepted standards are ARP 4754 at the system level, which defines it as a methodology to mitigate development errors. And our two item levels, so software is DO178, and that's guidance for production of software for airborne systems and equipment that performs its intended function. DO254, which is complex electronic hardware, which effectively is just software on a different type of hardware, is flow down of requirements to hardware and the fulfillment by the hardware of the intended function. I like to term it as a process to assure actual function matches intended function to an acceptable level. And one thing you'll notice is that the word safety is in none of these definitions. It's because these are not safety standards, they're development assurance standards, and they're about assuring actual function matches intended function. And if we look at our V diagram from 4761 or 4754, can't remember which one's out, you'll see that the safety process runs down the left and right sides of our systems engineering V, and development assurance runs across the bottom there, and at the pointy part of the triangle is the 178 and 254 processes. So system safety touches and interfaces with development assurance, but it doesn't drive into it. So we don't do things like software safety. We don't do safety down at the code level, the ones and zeros, purely because of the complexity and the quantity of the amount of software would be there. To do some sort of analysis on that, you'd be there till the heat death of the universe trying to look at 10 million lines of code. And so the way we kind of split these two domains in certification is system safety is really concerned about the function and its failure, the what is the system doing and what happens when it fails. Development assurance is more concerned about how do we make that function? How do we implement that in software? What tools and processes are we going to use to write those ones and zeros that go flying? And that's quite important when we talk about AI and machine learning, because AI is really concerned about function, whereas machine learning is really about how we make software. And we have to split those two out when we get into the certified aerospace domain. So just quickly, if we double click on DL178, just quickly, it's the means of compliance for software development assurance. It's two main processes, development and verification. During development, we want to make sure that we don't introduce errors as we take requirements and turn them into code. And then we run verification to detect any gaps, and it's all requirements based. There is a subset of DO178, so there's 4 levels in DO178, A through D. If we look at our V diagram here and overlay our different DO178 levels, we can see that DELs A through C are for our higher criticality software, and they push right down to the code level. So there's objectives that ask us to demonstrate compliance right down to the code level to the regulator. DEL D is for our lower criticality software. It actually doesn't push any requirements or objectives below that high level software requirement. So it's actually implementation agnostic. And on the hardware side, the equivalent of that, we're allowed to use things like off-the-shelf operating systems. Well, that's not hardware, that's software, but you're allowed to use off-the-shelf operating systems for DEL D projects. You can use multi-core computers, which are a lot harder to get into those higher level criticality systems. So it doesn't care how you make the software, largely that it performs the high-level software requirements and that it passes the tests, the requirements-based testing at that level and doesn't push any lower. And that's quite important when we talk about machine learning, and we understand that because machine learning actually operates down in that lower level part of software development. So moving on to artificial intelligence, this is the definition from EASA's concept paper around AI, and it defines AI as a technology that can, for a given set of human-defined objectives, generate outputs such as content, predictions, recommendations, or decisions influencing the environments they interact with. That's kind of a loosey-goosey definition, and it can be anything from a self-flying plane to a wet compass. So in the certified aerospace domain, it's kind of not that useful to us, and I'm not picking on EASA here. All definitions are kind of like that. They're very vague and waffly. So they become a little not that useful for us when we want to certify something. Inside that artificial intelligence definition is the thing machine learning and deep learning, which is really just more machine learning, and really there's no hard line about where that transition is. And when we're talking about development assurance, we're worried about how we're going to make this software, and so that's where we're really concerned about or want to look at machine learning, because it is a new way of making software as opposed to writing if statements. So really, in aerospace, I think we should probably steer away from using the AI term because it's too loose in definition, and we should really be using machine learning as our development assurance target. So what is machine learning? Machine learning is a software development process which we use to develop software to identify patterns in data. So instead of a human writing a bunch of if statements, we send a bunch of labeled data through something like a neural network, and the machine learns the patterns in that data to then apply that to new data it sees in that domain in the future. And this somewhat crass cartoon, which will probably get me cancelled, which I'm okay with, something, is kind of an example is neural networks are based on how humans learn. So basically when you're a kid or a child, young child, and when you see, taste, feel, or hear something in the real world, and some sort of authority tells you what that is, that's effectively labelled data, and your neurons make a bunch of connections. And then as you see something similar in that space again, some object in the world, and you get more information on that, you trim and prune those neurons and make new connections to further refine your mental model of the real world. And that's what neural networks are based on how they can detect data or predict patterns in data in the data it's fed, just like our Waymo self-driving car, and what a traffic light looks like and what it doesn't. It's that same process of building relationships in the data that it's fed, as opposed to writing a bunch of if statements and making a rules-based assessment on the data it's being fed. So just quickly, basically how we make machine-learned systems. We use a neural network. This is basically the concept of all these large language models that are being used and all this generative AI. In the background, there's one of these being used. Some of them with billions and billions of these nodes here. And they start with some sort of data set of labeled data or some form of labeled data. And they cut that generally into two. They have a development set that they train the software on, and then or the neural network on, and then they have a test data set that it hasn't seen before and run that through. And based on the outputs of that testing, they can make a statement around the applicability to the population data set. And so the better quality and more data you have in your development and test data sets, the better you can replicate the real world for when it sees data it hasn't seen before. There is two variations to this sort of approach, generally speaking. There's non-adaptive and adaptive. So both are made in the lab and developed, and then they're sent out in the real world. Non-adaptive systems are locked down and their configuration is locked and doesn't change. Adaptive systems have some sort of user feedback, so that as it makes predictions and it may get it wrong or it may make suggestions to the user can provide some sort of feedback, and that adds to its development data set, and so it can further improve its model of predicting things. And you'll have seen these things like Google has detected maybe spam has come through your inbox, and you might tell it, yeah, that's spam, or no, it's not. That adds that back into its development data set to make better predictions on spam emails in the future as it builds up that from millions of users. So I've quickly touched on assurance, and I've quickly touched on machine learning. If we smash those two things together now for 178, we've got a new way of making software. So how does our existing means of compliance work with that new way of developing software? So on the far right, you can see adaptive systems really kind of fall down for our airworthiness framework, because we're changing configuration, we're changing design, we're changing behaviour, and we would generally have to go back through the design process to achieve that, to continue its airworthiness. For non-adaptive systems that don't change once they leave the development environment, I've mapped them against the DO178 DEL's design assurance levels, and you can see A through C, there is really some challenges there, because as I showed in that V diagram earlier, They're really worried about the implementation and there's objectives that make you trace right down to the code. And that kind of breaks down when you use a machine learning development approach, because instead of tracing down to things like if statements, you're now tracing to a neural network with potentially billions of nodes on it. So that whole concept of DL178 breaks down. DEL-D, however, which is a very small subset of the other design assurance levels and its objectives, on our assessment, we believe that that can be satisfied because it is only concerned about high-level requirements, high-level software requirements, and verification of those software requirements, and it's implementation agnostic. So there's a small subset of our existing means of compliance which can work with machine learning and non-adaptive versions of that. Beyond that, it creates a challenge. So that challenge, so as I showed, some of the 178 DEL C through A objectives are not demonstrable to the regulator. And instead of its function being a machine learning system's function being coming from the if statements and logic that a human would normally write, instead it comes from the data fed through to that neural network and trained it on. And that really comes down to the data quality, the diversity and the quantity of that data. And that's one of the large factors in determining behavior of a machine learning system. And so therefore, machine learned assurance, I don't really have the answer here, I'm kind of describing the problem. Machine learned assurance is likely to focus on the data that is used to train a machine learning system and the gap between those development and test data sets and the overall population data set. And that can be quite a large gap when you think about the whole population data set of some sort of computer vision or natural language processing type machine learned application. And so at the top left there, we have our standard V model of DL178 when we're just dealing with standard traditional code. And we would have to look at supplementing that with some sort of supplement, like we do with, say, model-based or object-oriented technologies, where we look and analyze the data that we're using to train that neural network and train that machine learning system. So somewhere in there is the potential solution for how we get machine learning systems into higher criticality systems in aerospace. And there's a lot of work in this space, but generally by non-aerospace people, and they talk about things like AI explainability, AI alignment, AI robustness, and generalization. If you double click on those and have a look at what they're talking about and what they're trying to achieve with those things, they sometimes call it AI safety as well, it really is a development assurance process they're looking for. They want to make sure that that machine learned system will function as intended. It will do what we wanted it to do, nothing more, nothing less. And a little bit of sprinkling of human factors as we get more and more complicated systems based on machine learned development. So a quick run through. So software is the actual function, requirements are the intended function. Development assurance is about addressing that gap and keeping it to an acceptable level. Development assurance is how we develop complex things. AI is function, all about function, and machine learning is the development process. AI development assurance is really about machine learning. Non-adaptive machine learned developed systems can satisfy DL178 DEL-D objectives. Non-adaptive machine learned systems at higher DELs may be unable to satisfy some of the DL178 objectives, and this is where the challenge lies in getting machine learned systems flying. Ideally, or I believe, that machine learned assurance is about the gap between the development and test data and that real-world data. If we had all the real-world data to feed through a big enough neural network, we would get a perfect system. Unfortunately, that's just not practical. And assurance is really just part of the puzzle. We need to look at human factors, safety, and general certification, but I believe that development assurance is a large part of the problem that we have to solve. And that's it.